This wind turbine utilizes an ancient mathematical principle that is so remarkably efficient that it stands as the first machine to nearly perfect the capture of wind energy at a residential scale. This is the Archimedes wind turbine, and it generates less noise during full operation than a quiet conversation, poses no threat to wildlife, and in some documented systems, generates enough power to run a home at over 90% annual energy self-sufficiency. Yet, you have likely never seen one, nor are you likely to anytime soon. So, what exactly is going on here? What makes this turbine so superior to a traditional one? And why haven't they become the standard for off-grid energy solutions? To understand the brilliance of this device, we have to go back over 2,000 years. In the 3rd century BC, King Hiero of Syracuse commissioned a ship called the Syracusia. It was designed to be the largest vessel of its age, but its massive scale created an immediate problem. A hull of its size leaked water constantly, and evacuating that water manually required a workforce the ship could not practically carry. So, the king called on Archimedes, one of the greatest minds of antiquity, to solve this conundrum. And what he devised was brilliant: a spiral blade inside a cylinder that a single operator could turn to move vast quantities of water from the hull to the sea. This same device was adopted simultaneously in Egypt, where it lifted Nile water into irrigation ditches, defying gravity to transform arid land into productive agricultural ground, and later by the Roman Empire to drain groundwater from deep mineral mines. For well over 2,000 years, the Archimedes screw remained the global standard as the most efficient method of moving fluids with minimal labor. But in 2003, a Dutch inventor named Marinus Miramet reversed Archimedes' logic. Instead of a screw moving the fluid, what would happen when you let a fluid move the screw? Marinus Miramet had identified a gap in Archimedes' surviving mathematical works. While Archimedes had defined volumes for common geometric shapes by rotating them around an axis, he had not explored the spatial potential of the three-dimensional spiral as a rotor for energy conversion. Miramet's response was to transform the Archimedes screw into a conical spiral designed specifically for the turbulent, chaotic, direction-shifting wind of urban rooftops. The first patents for the resulting design were filed in 2006, and after a decade of field testing, manufacturing began in South Korea in 2016, producing what has become known as the Liam F1 turbine. But if you want to understand why the Liam F1 is far superior to the traditional bladed turbines for residential use, you first need to understand the shortcomings of traditional wind energy systems. Standard three-blade turbines are built on the principle of lift, the same mechanism as an airplane wing. They rely on smooth, fast airflow across the surface of a thin blade to create a pressure difference that drives rotation. That mechanism requires the wind to be consistent in direction and sufficient in speed. Below approximately 9 to 11 psi, most conventional turbines produce negligible power. Then, when wind direction shifts, the entire heavy body of the turbine must yaw to reorient, consuming energy in the process. And in the boundary layer of turbulent air that sits below 33 feet above an urban roofline, inconsistent speed and direction are precisely how the wind behaves. The result is a turbine that vibrates, produces the rhythmic thumping that drives noise complaints, and eventually mechanical failure without producing any real level of usable power. But the Archimedes turbine addresses these shortcomings using simple geometry. The rotor consists of 3 circular blades wrapped around one another and expanded along a horizontal shaft, forming a 3-dimensional conical spiral modeled on the Fibonacci sequence and the geometry of the Nautilus shell. This structure creates a pressure differential, not across the thickness of a blade, but through the spatial volume of the spiral itself. As wind enters the front of the turbine, The conical shape forces the air to accelerate along the surface of the blades, redirecting the airflow by 90 degrees as it passes through the rotor and extracting a large portion of its kinetic energy in the process. And this geometry produces three mechanical properties that conventional designs cannot replicate at the residential scale. The first is automatic yawing. Because the spiral is aerodynamically balanced, it orients itself into the optimal wind direction without electronic yaw motors or sensors. In an environment where wind direction changes every few seconds, this eliminates the energy expenditure and mechanical stress that cripples conventional turbines in urban conditions. The second is omnidirectional tolerance. Although it is a horizontal axis turbine, the Archimedes design can capture wind entering the rotor at an angle of up to 60 degrees from the axis. This makes it functional in the swirling, multi-directional airflow of an urban roofline, where a conventional turbine would stall. And the third is low cut-in speed. The Liam F1 begins generating usable power at wind speeds of 5.6 mph. Most conventional turbines of comparable scale require 11 planetranst of wind before they even begin producing a single watt. All this design theory is backed by real-world performance data. The manufacturer claims the Liam F1 achieves approximately 80% of the theoretical maximum permitted by the Betz limit, the physical law governing how much of the wind's kinetic energy any turbine can extract. Although independent peer-reviewed research and computational fluid dynamics simulations produce more conservative figures, the efficiency of the design remains approximately double that of conventional small-scale turbines. The most comprehensive independent testing was conducted by Pusan National University in South Korea across sites, including the typhoon-exposed coast of Incheon, where the turbine operated in conditions ranging from calm to extreme. The rotor demonstrated consistent self-starting at low wind speeds, stable operation in turbulent and directionally inconsistent airflow, and no structural failure under conditions that would disable or destroy conventional residential turbines. While in operational hybrid systems paired with solar, the Archimedes turbine has proven to increase annual self-sufficiency from 61% on solar alone to over 92%. This improvement came almost entirely from the autumn and winter months when solar underperforms. But the benefits of the shape extend just beyond mechanical efficiency. When it comes to noise pollution, the Liam F1 represents a significant reduction. A conventional 1.5 kW turbine reaches 65 dB in operation with that signature rhythmic thumping produced by air being clipped at the tip of each blade as it rotates. But because the Archimedes design has no blade tips, the result is less than 45 dB at full operation, comparable to light rain and below the threshold of a normal conversation. The impact on wildlife is also noticeable. Traditional three-blade turbines rotate at high RPM, becoming a near-invisible blur that birds and bats cannot perceive as a solid obstacle until it is too late. The Archimedes spiral is a solid, three-dimensional mass moving at comparably low angular velocity. It does not disappear into a blur. It remains a large, visible, slow-moving presence that wildlife can navigate around. Across more than a decade of field testing in environments ranging from the coasts of the Netherlands to South Korea, bird strikes on spiral turbines are documented as virtually non-existent. So, the Archimedes turbine is more efficient, quieter, and more durable than any other residential wind turbine currently on the market. So, why hasn't it become the standard for energy independence? The most obvious answer to this question begins to emerge when you start crunching the numbers on the return on investment. A turbine like this will cost you somewhere in the region of $5,000 to $7,000, and at average urban wind speeds of 11 mph, a Liam F1 system produces approximately 4,500 kWh annually, If calculated at the current American electricity rate of 15 cents per kilowatt, that represents annual savings of approximately 225. This equates to a payback period of over 20 years. In high-wind coastal environments where the turbine produces significantly more, the payback period compresses into the sub-10-year range. If you compare that to the average residential solar installation, which returns its cost in 6 to 8 years, for a homeowner making a financially motivated energy investment, the choice is obvious. Of course, there's more to this than a financial calculation. As we have already seen, those with the desire for a fully self-sufficient and independent power supply can utilize a hybrid system that combines a Li F1 and solar PV to create an off-grid, year-round energy supply. But upfront costs aside, regulatory frameworks can make implementing wind turbine tech in residential areas extremely difficult. Mounting a turbine weighing between 220 and 617 lb to a residential roof requires structural engineering certification to verify that the roof trusses can bear the load and the long-term vibration stress without fatigue failure, which is a lengthy and costly process. Homeowners associations can also be problematic, frequently prohibiting wind turbines, citing aesthetic concerns or anticipating noise and shadow flicker complaints. And unlike solar, which has been protected by solar access laws in several American states, small-scale residential wind has no equivalent legislative protection and is subject to the full discretion of local planning boards. But the supply chain barrier is also a problem. Solar photovoltaics has a mature domestic installer network, standardized equipment, and well-understood permitting pathways in most jurisdictions. The Archimedes turbine has none of these. There is no certified installer network in the United States. Most buyers must commission DIY installations, which require a working knowledge of three-phase AC electrical systems, MPPT wind charge controllers, dump load management, and roof structural assessment. Errors in any of these areas result in equipment failure, voided warranties, or fire risk from unmanaged electrical surges. The absence of a professional installation pathway means the technology reaches primarily technically literate early adopters, rather than the broader residential market. But for all those committed to integrating the Archimedes turbine into an off-grid or hybrid system, the starting point is a wind audit. The energy available in wind is proportional to the cube of its speed. A 20% difference in average wind speed produces a 72% difference in power output. Before any investment, an anemometer should be installed at the exact height and location of the planned turbine for a minimum of 3 to 6 months. The threshold for viable Archimedes turbine performance is a site average of 10 to 11 mm. Below that, the annual energy yield will not justify the capital cost in any reasonable time frame. Above it, particularly in coastal or elevated rural sites, and the economics become significantly more favorable. The turbine must be positioned at least 10 to 16 feet above the highest point of the roof, or any nearby obstacle to escape the boundary layer of slow turbulent air that forms around built structures. A turbine mounted at insufficient height in the turbulent zone directly above a roofline will produce a fraction of its rated output, regardless of the regional wind resource. For the structure itself, the Li F1 is the primary commercial product, typically costing between $5,000 and $7,000, including controller and mounting hardware. A smaller AWM 75PDD model, producing a maximum of $150, is available at a lower cost for battery charging in off-grid cabin applications. You should avoid low-cost spiral turbine imitations available through mass-market online retailers. These are typically plastic units with undersized generators that fail within months and have no relationship to the decade of aerodynamic development that makes the genuine Archimedes design function as documented. The electrical integration also requires some thinking and the acquisition of some specific components. A wind-specific MPPT charge controller is required to manage variable input and prevent overspeeding. A dump load, a bank of resistors capable of dissipating excess energy as heat, is also mandatory. When batteries are full, the dump load prevents the turbine from spinning without load, which would cause it to accelerate beyond its structural limits. For storage, lithium iron phosphate batteries are the preferred medium for wind systems. They handle the inconsistent pulsing charge profile of a wind turbine better than lead-acid alternatives, and a battery management system is required to protect the cells from high-voltage spikes during gusts. Ultimately, these turbines perform best as a component of a hybrid system, not a standalone energy source. Solar photovoltaics peak during summer daylight hours. The Archimedes turbine peaks during winter and at night. The two generation profiles are complementary, rather than competing. A 1.5 kW Archimedes turbine paired with a standard solar array creates a generation profile that approaches round-the-clock production across all seasons. As for maintenance, requirements are fairly modest. Bearings should be inspected annually. Blades should be checked for debris accumulation or ice buildup, which can unbalance the rotor. The braking system, which includes an electrical brake managed by the controller and a mechanical backup, should be tested annually to confirm function. The Archimedes wind turbine takes a 2,000-year-old geometric principle and applies it to generating usable power from the wind in the most efficient method that's currently available. Much of what we cover works exactly as claimed, costs less than what replaced it, and was set aside not because it failed, but because the system was never designed to accommodate it. If this story of ancient wisdom meeting modern energy has changed how you view the potential of your own backyard, please subscribe and like the video. We are dedicated to uncovering the history and technology that they tried to bury. Let's plant the seeds for a self-sufficient future together. Our next discovery is just around the corner.